Today we're going to get into the physics of matter, from the tiniest particles to the huge forces they can create. Okay, take a look at this. What do you see? You've got solid ice, a liquid ocean, and even gas in the form of clouds. And get this, it's all just water. So how is that even possible? How can one thing exist in three different ways all at once? Well, the secret is all down to the physics of its particles. So to figure this out, we're going to take a quick journey. We'll start with those tiny building blocks, then check out density and pressure. After that, we'll see what happens when you turn up the heat, and we'll finish by going to the coldest temperature imaginable, absolute zero. All right, first up, let's start with the absolute fundamentals, the unseen building blocks of, well, everything. So whether something is a solid, a liquid, or a gas, all comes down to how its particles are behaving. In a solid, think of them as being in a super strict formation, locked in place, just kind of vibrating. Now, in a liquid, they're still packed in pretty tight, but they've got enough freedom to slide around past each other. That's what makes liquids flow. And a gas? Oh, the particles are just going wild. They're super far apart and just zipping all over the place. And what's so cool is how these tiny, invisible arrangements lead to the stuff we can actually see and feel. A solid holds its shape because its particles are stuck. You can't really squash a solid or a liquid, right? That's because their particles are already right next to each other. But a gas? Totally different story. There's so much empty space in there, you can easily squeeze those particles closer together. And that idea of how tightly packed things are, well, that leads us perfectly into our next topic, density. Density really is just a measure of how much stuff, or mass, is crammed into a certain amount of space. And the formula couldn't be simpler. Density equals mass divided by volume. And of course, we can use this for real-life things. Let's get this iron block. We know its mass is 390 kilograms, and its volume is 0.05 cubic meters. So we just pop those numbers into our formula, 390 divided by 0.05, and bam, we get a density of 7,800 kilograms per cubic meter. Okay, so we've got how matter is packed. Now let's talk about the force it can push with. And that brings us to pressure. Pressure is a really interesting one. It's not just about how much force you apply, it's about how concentrated that force is. I mean, you can have a tiny bit of force, but if you focus it on a really small spot, you can create a massive amount of pressure. The formula says it all. Pressure is just the force divided by the area it's acting on. This actually brings us to a classic brain teaser in physics. Who do you think puts more pressure on the ground? A huge 40,000 Newton elephant or a 600 Newton woman wearing a pair of super sharp stiletto heels? What do you think? Well, the answer is kind of mind-blowing, and it shows this concept perfectly. Let's do the math. For the elephant, you take its massive weight and divide by the area of its big feet, and you get 400,000 pascals of pressure. Now for the woman. Her weight is way, way less, but it's focused on the tiny, tiny points of her heels. And when you calculate it, you guessed it, 400,000 pascals. It's exactly the same. And this isn't just for elephants and shoes, The exact same idea applies to liquids. The deeper you go underwater, for instance, the more pressure you feel. Why? Because you've got the weight of all that water above you pressing down. Simple as that. And you bet there's a formula for that too. To find the pressure difference in a fluid, you just multiply the height difference, h, by the fluid's density, that's the Greek letter rho, and then by the gravitational field strength, which we call g. All right, so we've got particle arrangements and pressure down. But what happens when we throw some energy into the system? Like when we start heating things up? Well, different materials react to heat in their own unique way. We measure this with something called specific heat capacity. All it means is, how much energy does it take to heat up 1 kilogram of a substance by just 1 degree Celsius? Water, for example, has a crazy high specific heat capacity. That's why it feels like it takes an eternity for a kettle to boil. And we can use this to figure out exactly how much energy we need. Let's say you want to heat up a small cup of water, about 300 grams, from tap temperature, say 15 degrees, up to boiling at 100 degrees. We just multiply the mass by water's specific heat capacity by that 85-degree temperature change. And the answer? You need over 107,000 joules of energy to do it. So, adding heat makes particles go faster, which in a gas means more pressure. That makes sense. But what about the other way around? What happens if we start pulling energy out of the system and make things colder and colder? Well, when scientists do experiments on this, they find a really clear pattern. If you take a gas, keep its volume the same, and just measure its pressure as you cool it down, You get this perfect straight line on a graph. As the temperature drops, the pressure drops right along with it. Super predictable. This straight line relationship, though, it brings up a huge question. I mean, does that line just go on forever? Is there a bottom? Is there a limit to how cold something can get? Here's the cool part. If you take that line on the graph and just extend it backwards, keep it going down, it actually hits the bottom. It hits zero pressure. And it does that at a very specific, very, very cold temperature, minus 273 degrees Celsius. And that temperature has a name. It's called absolute zero. It's the theoretical point where particles have the least amount of energy possible. For all intents and purposes, they've stopped moving. It's not just another cold day. It's the rock bottom, fundamental zero point of temperature. And it's so important that scientists built a whole new scale around it, the Kelvin scale. And the Kelvin scale is brilliant because it starts at this true zero. 0 Kelvin literally means zero thermal energy. It makes the physics so much cleaner. And switching between them is super easy. To get from Celsius to Kelvin, you just add 273. To go back, you subtract it. So, think about where we started. Just a simple picture of an iceberg. And from there, we've journeyed into the world of tiny particles, we've calculated density and pressure, and we've even found the coldest possible temperature in the entire universe. It just leaves us with one final, fascinating thought. We've found the ultimate cold. But is there an ultimate hot?